My name's Jim Lagree. I'm a Chief Engineer for Eaton Corporation. I want to talk to you today about arc flash mitigation techniques and considerations for your system design. My background is that I've been over 35 years working for Westinghouse and Eaton with their circuit breakers, trip units, protective relays, and other power distribution equipment. An arc flash is an unbelievable event. You just, when you witness this event, it really, the sound level is deafening. It's, it actually makes, when you look at the arc flash, it's like looking into the sun. The spots in your eyes last for minutes afterwards. And the pressure levels are just unbelievable. You really don't, I hope none of you really have to ever witness this. I've witnessed it under controlled conditions in our test lab, but definitely it's an experience to see one of these conditions live. So what I've done is I've kind of broken down arc flash mitigation into these several categories. Originally I saw this, a matrix like this done at an IEC standards conference. What it has is pre-arcing conditions where you have arc prevention and arc prediction monitoring conditions. And then once the arc starts, the arcing, what you can do, arc containment, and these are passive type of activities to take, and then active activities such as your arc detection method, which then leads into your arc elimination and your arc flash reduction techniques. So starting off, let's go to pre-arcing with passive arc prevention techniques. So the first one is, and I've seen this in several presentations here on, from EasyPower and everywhere else. Everybody recommends, if you can de-energize the equipment, please do so. There's no sense in working on it live if you don't have to, and so that minimizes the risks. Move people further away, closing and tightening doors and latches, and of course design the hazard out. Reduce the available fault current, and what we're going to spend a lot of time at the end there is faster clearing times. Faster clearing times are the key to arc flash reduction, and there's a lot of different. So well, this is one of my favorite photos that we use for training. And I would be that guy on the left, exposed, turning my head away from the arc flash, and guess what? Exposing an area that's not protected. You know, this is good practices. So it's so important to have good training and have your people trained in the right ways of safety practices. There's a ton of material out there. So for training, I know the NFPA has it. There are other sources that have it, and they've written very good standards that have a lot of good information. So the information out there is very good, and you should take advantage of it. Good design practices. Current limiting is always a good design. It'll limit that fault current. So this is the detection or the melting time if it's a fuse, or a circuit breaker actuation time, and then once it decides to open, that arcing time. So you're reducing the amount of fault current that flows into the fault. Good design racking. Here's, you know, again, a maintenance person who's fully clothed in the PPE equipment has to get to rack this breaker out, whereas there are robotic racking equipment and automatic rackers that are built into breakers, and so just good design if you can, if these types of devices are available. And now low voltage power air circuit breakers and now molded case breakers have racking capability. So you don't have to unbolt those devices too. Racking mechanisms are available. So let's talk about arc prediction monitoring as a pre-arcing, but more of an active action. First one, predictive monitoring. Let's partial discharge monitoring and measuring the integrity of the system, and the insulation integrity, and in all of your gear and equipment and loads, and transformer bushings. This type of prevention can detect here's a little corona discharge on a medium voltage bus, and before it escalates into a fault like this, you can detect that. So partial discharge monitoring is a great feature. Thermography, been around for a long time and used in a lot of places. Infrared windows in the gear let you do visual inspections, regular intervals. The only problem is it is a snapshot of temperature at the time of viewing. So, you know, if you happen to catch it, let's say that there's no load on a particular breaker or a bus, you may not see that temperature. But it's definitely been a good technique to use, and it's caught many things. I know the experience I've seen over the years. Here's a circuit breaker that in this terminal there must have been something wrong, and it was creating a hot spot that was picked up in the thermal image camera. The breaker was removed from service and sent for further diagnostic was the problem, but you just can't see that with the naked eye looking at the breaker. Acoustic Arc Detection is a new technology that's coming into to be used in the future, and a device like this that's mounted on the bus bar that's looking for the acoustic signature of micro-arcing inside that gear. So here it is, and just like partial discharge, this is only using acoustics to detect that loose joint or a micro-arcing or corona discharge that's going on inside that gear. That takes us to arcing. So here where the arc has occurred, what can you do? And some of the passive actions could be arc containment with arc-resistant and PPE equipment. So here are arc-resistant enclosures. Notice this explosion-proof device, the number of bolts that hold and contain the explosion, or if there happen to be an arc flash or an explosion inside that device, it can be contained within the enclosure. Here's an arc-resistant gear, and it's got a plenum where it pushes the arc flash up to the top and out the end of that plenum. And here's an actual picture at a test lab. Notice no flash, no arc, no burning or even lights coming out the front, and all that arc flash pushed out the side through that plenum. So what makes an arc-resistant testing successful? No indicators are burned. They're placed around the equipment. Doors cannot open. No projectiles from the equipment, and no holes are burned in the enclosure. And there's another example of it. And notice the arc being safely diverted away from where people might be standing. And of course, your PPE clothing. It's important to understand what your PPE calculation is and how that relates to the type of clothing that should be worn. There's no sense in wearing PPE 4 if your hazard is way down here where you could just use cotton clothing. So then let's talk now about arcing and active systems to do that. And the first we're going to talk about is arc detection and the different systems for detecting arcs, which will lead us into arc elimination and arc flash reduction. So first, talk about line-to-line faults. This is what we do in the lab to get the maximum amount of current flow when you have a bolted fault current. and there is the least amount of impedance between like a circuit breaker and where this fault is located. But what really happens in the real world? Is it a bolted fault? It could be. And is this wrench laying across the bus, will it create as much current as a bolted fault? Probably not. And will it bounce off there? Will part of it weld? Will it only weld between two phases? That's the unknown of arcing faults and what can occur with arcing faults. So there are, you have to understand that really in your equipment, you could have the range from the full bolted fault current flow to a very high impedance, lower arcing type fault. And so let's start off with arc detection AFCI. Many of you have heard about AFCI. It's required in your home in most of the states across the country. It started as more of a residential. The UL standard is 1699. They have this is basically your your standard thermal magnetic breaker with arc fault technology built into it. So it has the the overload protection and the short circuit protection coupled with usually an electronic PC board that detects the arcing condition. There are some designs out there that contain 20 milliamp ground fault protection. Though the standard doesn't require it, some companies have added this, and it's an added feature because it detects ground fault arcing conditions also. So AFCI, AFCI can be broken down into parallel and series arcing. And let's take parallel arcing is a fault between the line and neutral. So here's our AFCI breaker. There's our power source, and typically there's some cable impedance. And in many homes, that is a lot of impedance that has choked down the available fault current at this point. And so you can see what's happened. Here, this is a sputtering parallel AC arc waveform, and it's not a full AC wave. It's just a sputter of an arc. Here's another spike, another one, and then it goes out for a while. This will not trip a standard thermal magnetic breaker because there's not enough RMS heating current for an overload trip. And because of the impedance of the cable, the peak of this current does not get up to the instantaneous rating of the breaker. And so that's why parallel arc detection is one of the features of AFCI. And it looks for the slope of this waveform because it's not a normal AC sine wave and it detects the steep rise of the parallel arc waveform and trips on it. Then there's the series arc. And series arc's detection actually came after the parallel arc was first released. I think it was called a branch feeder. Then series arcing was added later. And series arcing is a lot tougher to detect. The algorithm for a series arc needs to look at what is a good arc versus a bad arc. Yeah, and I say that because guess what? In your home, there are lots of good arcs, or let's say controlled arcs. When you flip a light switch on and off, believe it or not, there is a little arc drawn between the contacts of that light switch. You pull your kids or somebody pulls the plug out of a receptacle and draws an arc from the receptacle to that. It's not a dangerous arc at that point. Probably will go out if not around any combustibles. Won't cause a problem. Or the bimetal on a skillet or a coffee pot will open and close as it heats up the temperature and regulates the temperature. Well, as that bimetal inside that let's say skillet opens up and then closes, then opens up again, it draws an arc inside there. compressor will look like an arc when it starts up. There are some lighting fixtures that look like arcs when they get turned on. One of the biggest problems we first detected was an incandescent light bulb, when it burns out, actually looks like an arc. It has an arc signature to it. And so we had to design around all these types of naturally occurring arcs that you didn't want to trip the circuit breaker on. And you can see this is the current signature waveform that has a series arc in series with it. And so there's an impedance built across here that's creating these shoulders in that AC waveform. And so there's very sophisticated algorithms that are used to detect whether this is a bad series arc or a naturally occurring thing that happens. So I think this slide just repeats all that information I just told you. So there are okay arcs and there are arcs you need to detect and trip on. And that is really the technology that's inside that AFCI breaker. Ground fault's a very good method of protection, and it can protect against arcing faults to ground. So and today you can get what we call equipment protection in some of the smaller miniature circuit breakers. Personnel protection, the National Electric Code and the UL standard says it has to be less than 6 milliamps sensitivity to protect people. If you're living in an IEC country, the standard says it's 30 milliamp sensitivity should be used. And high resistance grounding is getting a lot of good publicity too, because with the high resistance grounding you can limit the level of the arcing current and lower the detection level where it is, so from the equipment. And this is used, I know, a lot more in the system design. Arc flash light detection relays now are becoming very popular. This is where you have a device that will detect the light output of an arc flash. It's and then it can couple that with phase and ground fault currents to say, I see a high ground fault current or a phase current, and I see light, then I will send out a trip signal. So there's devices that use only just detect light. So selectivity, you can have these sensors in different areas of your switchgear. And then you can have it optional, whether it's current and light or just light. And they're all full supervision, where they are constantly checking themselves, checking the sensors to make sure that they're all properly working. So where's the light? Can be detected using plastic fiber or glass fiber sensors, or they can be point sensors. This is a point sensor, and right here is the sensor on the top of the module. In this particular relay, you can link 3 of these up on one channel, and there are many channels in the relay. The nice thing is it's current signaling based, so it's noise immune. They're cables. So if you're shipping equipment, one thing is very tough is trying to run that fiber optic cable between shipping splits or between the switchgear. And with this, when it's electrical signal, you can have plugs and run the shielded cable between the switchgear. Oh, and then they also come between 3 different light intensities. You can buy them, and so they'd be real sensitive to lower lights or very resistant to outside light and looking at a very higher lux, and 3 different styles that way. So you get 180 degrees of visibility from this point, whereas the fiber gives you 360. It is all around that fiber. This is just for your switchgear optional. It's whatever works in your system, and more options or more capability is better. So three-phase current detection. Here are relays that have current and light. These are light-only type relays. You can have point sensors, or you can have fiber loop sensors. So here's 3 channels on that, 12 sensors on this particular relay. And then from that relay, we want to, and for a system design, we need high-speed outputs and for tripping, and we also need inputs for receiving signals from other light sensors. And how this works, if you're using light and current as the mechanism to trip it, here's an example where this is maybe just background light, and the level we're using an 8,000 lux sensor, and that's the trip point of 8,000 lux. And maybe this is just background light, and all of a sudden it gets a little brighter, and at this point it has crossed the 8,000 lux point. And also it's saying I'm going to AND that with current. So it's looking at the phase current, and this is normal phase current. All of a sudden the phase current accelerates, and as soon as the light has reached that point and the setting for your current trigger have been both reached, that's when the trip signal is set out from the relay. And then you can from there that can trip a circuit breaker or a quenching device. So here's a main system, and we've got light and current sensors here, and we've got just light sensors down here. And you can see this system's been segregated into zones. So I've got a zone here, S1. It's looking for upstream from this circuit breaker, and between the transformer and the circuit breaker, it's looking for arc flash light in that zone. And so you can set up logic inside this device that will detect on S1. If light is only on S1, send out a signal to trip the upstream medium voltage circuit breaker, and that's what this T2 signal is doing. Here also we can have a sensor S2 on the circuit breaker in the circuit breaker compartment. Meanwhile, S3 is in the bus below on the load side of that circuit breaker. And what we can do there is if we see light on S2 or S3, we can trip circuit breaker CB1B with T1. And maybe if we only see light on S2, we may trip 1B and CB1B, where this could be lighting, or this could be a fault inside the circuit breaker or slightly above the circuit breaker in this zone. So that's where you could segregate for selectivity these different sensors to get that separation. And then these sensors here say, oh, here's this particular light relay has S1 just on the load, S2 is on the breaker and the bus, and he can say, oh, I see light, and if it's only on the load, he's going to trip CB4B-3, and whereas this relay will hold off from tripping CB1B because he knows that this light sensor is going to trip that feeder breaker and remove the fault that occurred down here. So a very nice system that can be set up to communicate between all these different relays and set up a nice selective system in your gear. And here are just pictures of sensors on the top of the gear. These are point sensors on the top. And over here we have a fiber optic sensor that is snaked around the the outside of the, well, the inside of the gear, the door, or the equipment. So either way, we've tested both and found out that whether it's a point sensor or it's a fiber sensor, that all the tests that we've run have both been picked up by both. We didn't see where we found a spot where there wasn't one that didn't pick up or the other. An important part to understand too, if you're applying these light sensing relays to a low voltage system, low voltage circuit breakers interrupt the fault in air. And what is created is actually a controlled arc inside the circuit breaker. As you see in this diagram, this particular, the arm of the circuit breaker and that particular phase opens up, and the arc then is pushed into what we call the arc splitter. It is cooled and divided, and that's what really puts out the arc. And so guess what? What happens is in an arc flash condition, a circuit breaker will put out arc flash light. So if you do not want to trip the upstream breaker on the light produced by a circuit breaker that is closest to the fault and interrupting to clear the fault. And so here's a condition. This green light, if you can see it, is a trace, is the fault current. And the pink line is light detected by the light relay. So a fault occurs at this point, the fault current goes up, and guess what? There's no arc flash. There's the pink, the arc flash sensor does not pick it up, and so the relay does not see anything, but there's high current, and the breaker at this, sometime around this point, decides that it's taking out this fault, and it starts to interrupt, and then suddenly there's an arc flash coming out of the arc chutes of the breaker. And as you can see, as the breaker starts to open up and part and clear the fault, an arc flash is created and put out, and guess what? The light sensing relay sees it. So here's really, you don't want a nuisance trip on the light from a breaker that is doing its job and interrupting the fault. And so there are ways to prevent this, and one of them, some of these relays have a time delay where you can set up a restraining signal that says if you see light within this certain period, and it can start at a certain period of time and say, this is when the circuit breaker is going to has detected current and is going to open, and from this period on I'm going to put in a restraining time delay. And this is available in some of these relays, and it's a great option to have to prevent nuisance tripping just caused by normal arc flash coming out of the arc chutes of the circuit breaker. And that's an air circuit breaker on low voltage. So what do we have? This is a build chart that we'll build as we go through systems. Here's our first system. We're calling it light sensing tripping of a circuit breaker. So what happens? Within 7 milliseconds, our light sensors have detected light and initiated the light relay to shunt trip a circuit breaker. The shunt trip coil is energized. It takes about 35 milliseconds for that coil to be energized and to get the whole mechanism of the breaker to start opening. At this point, 35 milliseconds later, the breaker contacts have parted and are drawing an arc through the arc chutes. And it takes for a large fault, it takes about 13 milliseconds for that arc, that arm to go all the way up, and that arc to get into the arc chutes and cooled by the arc splitter, and eventually you clear the fault. So your light sensing tripping of a circuit breaker takes about, and these are typical times, 52 milliseconds to interrupt. So let's look at arc elimination. We've detected and light sensing, we used that to interrupt a breaker. Let's look at shorting bars, arc mitigators, and creating parallel arcs. They're active devices when we have an arcing condition. So an arc quenching device is a shorting bar. This is a device that is below a circuit breaker, and it creates a three-phase short circuit when an arcing condition is detected. So in this case, this device is fired by light and current and will create this short between all three phases, and basically extinguishing this arc fault down below, because all of the current from all of the phases will now flow through created arc fault. So happens very fast. It's a device that can eliminate an arc in a very quick period of time. But the problem is typically this device has to be replaced, and you put a lot of strain on the upstream system, whether it's a transformer up here, the circuit breaker, because now you've created the highest level of current that this breaker can actually attain, because you are putting a volted fault on the end of that breaker. There's no other impedance that could limit this condition. And so this breaker will see its maximum current that the upstream transformer can provide it. Another device similar to that, quench the arc with an arc. And one of my physics friends told me that there's actually a physics law out there that says two arcs can't occur in parallel. Only one, and probably I think it's the lowest impedance, will survive. So if you have an arc downstream here in this device, and you had a device where you can create an arc, and then all the current will flow through this arc and not through this arc. And essentially you're quenching the arc fault downstream. So because you've created this arc, there's more impedance in this arc than it is a shorting bar. And because of that, you're putting less stress and strain on the upstream devices, the transformer or the circuit breaker that will eventually clear this arc. And so this is an arc that quenches an arc, but it's an intentional arc. And usually they're contained inside a vessel that can hold and has been tested to contain this phase-to-phase arc. So where's our quenching device land? Very fast. So typically 5 milliseconds after the fault occurs. Here's when the fault occurs. 5 milliseconds, could be 4 to 7 depending on the device. The short circuit is eliminated. Now you have about another 32 milliseconds where that created fault is then cleared by that upstream breaker. So you've created a fault at this point. You've put out the dangerous arcing fault. Now you have the controlled arc that has to be eliminated, and that clears about 32 milliseconds later. So the quenching device is probably one of our fastest devices that can be used to eliminate an arc. So another one is arc flash reduction. And again, the arcing condition has occurred. These are more active systems. So let's look at that. And as a matter of fact, they're all listed in the National Electrical Code 2014 section 240.87, method to reduce clearing time. There's our clearing time again. So this is, we want to eliminate an arc as fast as we can, less arcing and less time the fault is there, there's less arc flash that is exposed to personnel or equipment. So the first one is zone selective interlocking, and let's take that. First of all, I've worked with curves for years and years and years, and I've never seen them scrutinized so closely in these past few years. We never really expressed a zone selective interlocking clearing time before, kind of vaguely put it into time current curves and said, we know it's going to go faster than the short time delay. Well, you know, that just isn't good enough anymore. You have to be very specific, and as a matter of fact, on one of our breakers, we actually tell you whether or not for 60 hertz versus 50 hertz, what the time delay may be. So these curves now, which used to be looked at with just the naked eye, now are looked under microscopes. People are looking for trying to get as close protection as possible with each curve and maximize their system. So there's nothing wrong with it. It is just better design now. So zone selective interlocking, a system or a feature designed to reduce thermal and mechanical stress on electrical distribution equipment during short circuit or ground fault events. ZSI permits the nearest upstream circuit breaker to a short circuit or ground fault to clear the fault without intentional delay while maintaining system coordination. So what do we have? So this is an example, zone selective interlocking example, and there's our zone 1. We've got a zone 2, and then we have a zone 3. And what we're going to do is show that here's our green breaker has a 300 millisecond time delay on our short delay. Our blue breaker has a 200 millisecond time delay. And then our gray breaker has a 100 millisecond time delay. So we're effectively coordinated and separated. We have then a fault. Let's say a fault occurs here down at 3, which is our zone 3. And that fault current occurs at this level, and it's going to trip around 100 milliseconds. And what we then have is, because there's no zone below this breaker, it doesn't get a zone selective interlocking signal from anything below. And this device then says, I see the fault current, and sends a restraining signal to the blue breaker. Then the blue breaker sends a restraining signal to the green breaker, 3.1, and says, I see the current too, so restrain. So these two breakers are restrained, while the gray breaker doesn't get a restraining signal from anything below it, and it says, I must be the closest one to the fault, so I will trip immediately. And it trips, instead of waiting 100 milliseconds, it trips in 70 milliseconds. So you saved a little bit of time, and so now it can save 30 milliseconds of extra burn time for that fault located in this position. Now, here I have a fault that occurs in position in 2, which is zone 2. this breaker sees the fault current. It sees the fault current flowing into that fault and sends out a zone selective interlock signal to the 3.1 green breaker. It says, I see that fault and don't trip, I'm going to take it out. Because it doesn't get an input signal from the gray breaker or this white breaker below it. Neither one of those breakers see this current or this fault current that's flowing into fault 2. And instead of tripping at this 200 milliseconds, it then trips at 70 milliseconds. So it has saved this amount of tripping time. It has saved this amount of tripping time. Instead of waiting for that 200 millisecond delay, now it says, I'm the closest one to the fault, I'm going to take it out, and it goes immediately, and you've saved that amount of burn or equipment damage that can occur in your gear. Now, here's a device. It happens on this bus in zone 1. I have a fault right here on this bus. Again, and it's a much higher current. It occurs way out here, and guess what? It could be up to 300 milliseconds because that's the selective coordination time delay for this breaker. So this breaker would normally wait 300 milliseconds before it would trip, but with zone selective interlocking at this level, neither the blue or this 2.2 white breaker have sent zone selective interlock signals to the green breaker, and so there's no input on the ZSI circuit. So it says, nobody below me sees it, but I see it. I'm going to trip immediately now, and so what does it do? It trips now in 70 milliseconds instead of waiting all this time, and you have that large amount of burn time that or fault time that's been saved. So that's a very a critical thing that to understand, that a good zone selective interlock signal can save a lot of fault arcing time if properly coordinated. ZSI considerations. So when you're doing a zone selective interlock design, one is the number of devices. So you've got to understand that those are signals that are all connected together. Different manufacturers have different systems. There are usually a limited number of devices. Auxiliary power as a requirement. There are systems out there that require auxiliary power to power the ZSI system. In that case, then you might need a UPS system to power that auxiliary power. There are other manufacturers that do not require auxiliary power, and they work from the fault currents that producing a power supply and the signal to drive the ZSI from the current transformers of the fault current in the system. The length of each run. Again, this is a communication system, so the wire is an impedance, and that level of signal may degrade if you run this too far. So the wire, there's resistance, impedance, capacitance. It's a transmission line, and you've got to be aware of what is the length of the run. And the other thing is compatibility with other protective devices, such as medium voltage devices, other protective relays, other types of protective devices, whether old or new, and how you're compatible. Are these zone selective interlock communication systems compatible with each other? One thing about ZSI terminology, I'm a real perfectionist. I like to think about the terminology used. Instantaneous. The definition of instantaneous is a short circuit protection without an intentional time delay. So no intentional time delay is intended with instantaneous protection. So So there's a system out there, somebody is saying they have ZSI on instantaneous. How can you have an instantaneous with a restraining signal? Then it's an intentional time delay. It's not a true instantaneous. Now, if you want to call it a second short delay, that's fine, and that works for some systems. That's great. You know, more choices is what this is all about. And if a second short delay ZSI time is good for protection of your equipment, great. You know, use it. But I just like to straighten out the terminology because truly an instantaneous can have a training signal or a time delay associated. So what's our zone selective interlock look like? I've worked with trip units a long time, and as opposed to protective relays that need auxiliary power, an electronic trip unit powers up from the currents and the current transformers or the currents that run through the breaker, and it takes a little bit of time for the electronics to power up. So 4 to 6 milliseconds for the electronic trip unit to power up, and typically there's about 21 milliseconds of processing time in the short delay, where then it sends out a zone selective interlock signal out. And so this is where the communication handshaking takes place, and you want to make sure that you're not operating on just a transient or a false indication. So usually there's some filtering, and maybe I send out a second signal and read it, or read that input signal again. So probably about 37 milliseconds later, the trip coil in the circuit breaker is engaged. At this point, the trip unit has engaged the breaker to tell it to open. It takes about 16 milliseconds for that breaker to open. Once the mechanism has moved, then it probably takes another 13 milliseconds for that arc to be extinguished. So the arm is rising up through the arc chutes, and eventually when that whole arc is totally cleared, that's like 13 milliseconds later, typically we'll have about a zone interlock time of around 70 milliseconds. So that's for, and these are for low voltage power breakers. If you did this for a molded case breaker, those times would probably be shorter, the molded case breakers being quicker. Differential relays are number 2. Similar to zone selective interlocking, basically you've got a differential relay that's looking at the difference of the current flowing between two nodes. And again, it's a method to detect, to have a zone of protection and to trip really fast. Again, different configurations to detect or set up for a zone. So it measures the current going into and out of the zone, and they must equal. If they're not balanced, if there's a differential, then it will trip. And I put this in with software instantaneous. Software instantaneous is like a very similar, because there's electronic trip unit, it powers up, and then again, if this was a protective relay, you could go on a UPS power or something like that, but you can't always guarantee that that type of power is available. So, and like in our trip units, they're all powered from the currents that flow through the breaker. And so after that, there's probably about 25 milliseconds of doing this instantaneous trip where you're sampling currents, summing, squaring them, getting the true RMS value to make sure that you're just not going on a peak value that might be a transient or some kind of surge current. And then saying, okay, I'm over, and measuring that versus your setting. So am I over this current setting that the customer has set? And at that point, you engage the trip coil inside the circuit breaker, the mechanism has to move, and then the breaker contacts part. Eventually the fault is cleared. So that takes about approximately 58 milliseconds to happen. On some breakers that can be lower, much lower, typically, or it could be slightly higher for a maximum. So there is a tolerance, because you don't know, like this 25 milliseconds, I'm just picking an average, but it could be a little bit more, it could be a lot less, because it depends on where you're at in your sampling cycle. And our third system is an energy-reducing maintenance switching with local status indicator. So we've got this maintenance switch and an indication of it being engaged. So in this particular, here's a trip unit, and in this white area is the arc flash reduction maintenance switch. It uses a separate bypass path that is strictly analog. So there's a separate analog microprocessor involved with this. It doesn't use an ADD converter. There's no code to be executed, and it can trip it much faster than the normal trip unit. The blue LED tells you that when it's engaged, when you turn it to the on position, the blue LED comes on to tell you, as feedback from the trip unit to tell you that it's engaged. There's a 5-position reduction setting. And I know several of our maintenance people, we have an engineering service organization, and they actually requested this. And they said if they're working on a system and they know they have to keep the power on, but they don't want it to nuisance trip if there was like a motor startup. So they set this to the level of instantaneous current that the load, or that there may be, like, such as a motor that starts up. And so you can vary this from 2.5x to 10x the rating of the breaker. And that's the pickup point where the trip unit will say, okay, now I'm going to trip on maintenance mode. Remote indication. Nice to have a relay associated with that, so you can put it outside and indicate with a separate light or annunciator if you're in the arc flash mode. Remote enabled, it can also be done via communication. And of course, lockout tagout. You can either lock out the face of the trip unit with the plastic cover and a seal, or lockout tag out the remote switch like shown here. This is, a lot of people have asked me about the time of a circuit breaker. So this is a great example of it. Here's a main power breaker feeding a whole bunch of multi-case breakers. And let's say you had to do maintenance on one of these breakers. Well, if you shut down this breaker, it shuts down all these feeders feeding whatever load it is. And if you had to work on it live, then you could put this breaker in the maintenance mode, and that protects all that downstream to all of these feeder breakers. So now you can work on this with the knowledge that you're in the maintenance mode. It's going to be a much reduced level of arc flash should there be an accident that occurs. And this just shows you some of the wiring, how the inside of the trip unit, there's a relay that can give you this indication of a blue stack light. The nice thing about that is it tells you that it's in the mode. It also tells you, so you have that confidence. Number two, you won't leave it in the arc flash mode because you've got this indication telling you that, so you know that when you're done with your maintenance, to go back and turn it out of the maintenance mode condition. And as I mentioned before, there's 3 different ways. Face of the trip unit can turn it on or off, the remote switch, or communications. And we've tested this in our lab, and there's an IEEE 1584 standard that tells you how to do this arc flash test. And basically, they've come up with this 7-calorimeter array that simulates the body torso. You've got this steel box with the front face open, and these calorimeters measure the arc flash that flows out of this box. Inside the box are 3 conductors, and they're all shorted together with an 18-gauge wire. So the circuit breaker that we test is placed up here, and we put it in normal mode or we put it in the arc flash mode, and then engage the source, the lab source, and that's when the fault current flows through the breaker into this fault, and it's measured with this calorimeter array. So, and here's an actual picture of the test. Here, this is the breaker that's under test. Here's the cables to the 3 conductors go into the box. Here's the open front end of the box, and this is the calorimeter array right here. And this is some testing that we did with molded case. Same type of testing. There's a close-up of those 3 conductors with the short between. So ARMS is a separate bypass, strictly analog. I think I've covered most of this. And the good thing is that you can, if you use that remote switch, it can be locked and tagged out, and there's no need for recalibration. Because, and here's another slide just to show you that maintenance modes now, even in molded case breakers. Because of the National Electric Code, we didn't think we needed it in smaller breakers. Many customers now are asking it into smaller and smaller amperage breakers, no matter what level, even below the NEC level that it's required in. And here's what I wanted to say. This is the maintenance mode curves. This shows you a typical one line, of a curve for a circuit breaker, and your typical long delay, short delay, and instantaneous pickups. And what happens when you put it in the maintenance mode? A 2.x, basically a straight line curve is produced and overlaid over the existing protection. So the long delay pickup and part up to the 2.5x of the long delay protection is still there. It's not until the 2.5x that the maintenance mode picks up and trips. And so it will trip before the rest of this protection is engaged. But believe it or not, both systems operate in parallel. Both systems are there. So where is our maintenance mode switch? We have 4 to 6 milliseconds of power up. That's when the analog power circuit powers up. Then it immediately engages the trip coil. You've got about 16 milliseconds where the breaker mechanism opens, 13 milliseconds parting the contacts and clearing the fault, and typically you'll have around 33 milliseconds of arc trip. So nice slide. I put this together just to give you an idea of all the different methods out there and the different types of trip times that you can get, because trip time equals arcing time. There's less arcing time if you can trip sooner, and that reduces your arc flash, reduces your calorie count, and it's a safer condition. So, sum it all up, it's quite a landscape of arc, but I kind of like this slide too. It gives you a very broad overview of passive, active things you can do before arcing condition, or types of systems that you can enact to reduce or eliminate arcing once it starts. So that's the end of my presentation, and we'll open it up for questions.